Okay, question number 2, sorry. This will be published on Tuesday, which is on 1st October. Okay. Now, the first diagram shows a person standing on a turntable which can rotate freely. Okay. The person is stationary and rotates a bicycle wheel. The wheel rotates anti-clockwise when seen from the above. Okay. So as you see, he's standing on this one, and this is now rotating. He holds it like this. As a result of it, as it rotates, and then what you do is he flips the wheel. He flips the wheel. Okay, that's what it is. The wheel is flipped as shown the diagram, and so it rotates clockwise when seen from the above. Okay, so initially it is rotating like this. When you flip it, it will rotate like this. Oh, I did not start the timer. Right. Okay. Explain the direction in which the person-turntable system turns to rotate. Okay. Now what is happening here is that when you have something rotating, about an axis, let us say for example, if it is rotating in an anti-clockwise, as you see from there here, okay, if I see from here, so it is rotating in an anti-clockwise direction. When I see from the top over here, okay, when seen from the say clockwise, I'm sorry, so it rotates clockwise over here. So when I look like this, I see my finger is pointing downwards. I'm doing my right hand with my right hand. So as a result of it, finger is pointing downwards, which means this will be your angular velocity. This will be your angular velocity, and I times angular velocity is nothing but your angular momentum also. Okay, thus the direction of angular velocity and angular momentum are the same. Okay. Now what you did was that earlier when the wheel was rotating like this, then what happened? You were stationary, and the angular momentum was in this direction. How do I know? See, I keep my fingers like this over here, right? I keep my fingers like this. So the wheel is now rotating like this. Angular velocity is directed upwards over here. So this means angular momentum was like this. This was your angular momentum vector. Now we know from conservation of angular momentum, when no external torques are being applied, angular momentum is conserved, right? Which means in order to conserve it, if I flip the wheel like this, then what can happen? Okay, so I am changing my direction of angular momentum. So now for the net angular momentum to be 0, what should I do? I should impose, as a person when I am standing here on the turntable, I am also free. So what happens is I should be rotating in the opposite direction, right? So I should be rotating in the opposite direction. So therefore, so first there are, how many marks is this? This will be for 3 marks. The first you should write to satisfy conservation of angular momentum, the system needs to rotate in the opposite direction. Second reason what you should say, or maybe, okay, first reason, actually this should come to third one. Okay, so first reason what you should say is that, let me write this 1 here, let me write this 3 here. Okay, this is the conclusion what you have. First reason, because 3 points, right? So you should write fully. First reason is that angular momentum initially is in downward direction. Second reason, to compensate for it, the person should rotate in the opposite direction. What do you mean by opposite direction? Which direction should you rotate? That's what has been asked. Explain the direction which it should rotate. Now it is moving in a clockwise direction, and hence the person should rotate in. So the person should rotate in clockwise direction, anti-clockwise direction. Okay, the wheel is rotating in the clockwise direction. The person should rotate in the anti-clockwise direction. Okay, so this is what you need to mention. Okay, let us move on to the next. Sorry, we still have some more questions. Just a minute. Okay, explain the changes to the rotational kinetic energy in the person-turntable system. Initially, so what is happening to the kinetic energy? Initially, what happened was only the wheel was rotating like this. He was holding it like this. So therefore, the initial kinetic energy was only due to half I omega square. Let me write this as wheel square. Now, when he took the wheel and he flipped it like this, what happens? Okay, he also starts rotating, and the wheel also starts rotating, right? So which means The final kinetic energy would be half I into omega person square plus this is I person into omega person square plus half I into half I wheel into omega wheel square. Now if you ask me, is it that okay an energy is being created because you flip the wheel? No, wheel energy is not created here. While you rotated the wheel, you did some work extra. Okay, that extra work is being reflected as in the rotational kinetic energy. Remember, by rotating the wheel, you are not creating any extra energy here. Okay, so which means that the wheel, when you rotate it, initially let us say it was rotating at something like 5 radians per second. Okay, the angular velocity of the wheel. When you rotated it like this, the wheel that now will not rotate at 5 radians per second. It might rotate with something like 4.8 radians per second. And at the same time, you also did some work here by rotating, right? That work will add on to you, and hence what happens is you will be rotating with a small angular velocity. Okay, so you're not creating energy, not destroying energy. Energy conservation is perfectly valid here. Okay, now let us move on to the next one. Okay, so this is a different question, but anyway I want you people to solve it this week itself. Okay, so now let me move this timer a little bit away so it doesn't obstruct my question. Right, a solid sphere of radius r and mass m is released from the rest and rolls down a slope without slipping. The vertical height of the slope is h. Okay, moment of inertia I of the sphere about an axis through its center is 2 by 5 mr square. Moment of inertia is given. Then what is he asking here? Show that the linear velocity v of the sphere as it leaves the slope is root of 10 gh by 7. When it comes here, it moves like this, right? This velocity is this value. That's what has been asked. So how do you do? Simple work. Use conservation of energy. Okay, so what is the energy at the top? What is the energy at the top? The energy at the top, let me call this position as P, call this position as Q. Energy at P is equal to mgh, nothing else. It's not rolling, it's not moving, nothing, mgh. Then energy at Q, while it came down, how did it come? It did not slide. So it actually started rolling, but the center of mass also started moving. So therefore, F half mv square should be the energy of the center of mass while it rolls, plus the half I omega square should be the kinetic energy of rotation. So thus, this should be half mv square plus half into, what is the value of I? 2 by 5 mr square into what is omega? V square by r square, because no slipping, right? So this r square goes away, this 2 goes away. So you get this as half mv square plus 1 by 5 mv square. So when you take the LCM, this will be 10, 2 5s are 10, 5 1s are, plus 5 2s are 10, 2 1s are. So this should be something like this, 5 by 5 plus 2 divided by 10 into mv square, which should now be equal to 7 by 10 mv square. What is there on the left hand side? What is there on the left hand side? Nothing. Okay, so you have EQ here. EQ here. We know that by conservation of energy, EP is equal to EQ, right? Potential energy has got converted into kinetic energy. So which means now what I will do is I will just equate mgh is equal to 7 by 10 mv square. This m and this m goes away, which means v square is equal to 10 gh divided by 7, or v should be square root of 10 gh by 7, right? So what is being required? Root of 10 gh by 7. Thus we are able to prove this. Okay, so with this we come to an end to the second question also. Okay, so see you in the next week's questions. Thank you.